I would like to welcome you to today's webinar, where we look at the topic manual versus automatic step testing. Let me introduce myself. My name is Leo Lategan. I'm APC consultant at IPCOS and have been doing that for the last about 6 years. Before that, I worked for Aspen Tech for about 10 years. So in total, I got at this point about 17, 19 years of APC experience. I participated in quite a number of step tests, so I hope that I can give you some hands-on advice on this topic today. Okay, just to introduce you to our company IPCOS, we consist of 2 business units. As you can see there, the one is digital oil fields, the other is plant operations excellence, and it is under this division that the APC activities are housed. Amongst other things like alarm management is also one of our activities. IPCOS has done over 500 projects in about 50 locations in up to 30 countries. In total, well, we've got about an average of 15 years of experience amongst our more or less 65 engineers. We've got offices located in Europe, currently also in the USA, in India and in the Emirates. Okay, so let's start on our topic. The first question that I would like to ask, what is the purpose of a step test? Mainly that is to generate rich enough data that we can use for model identification of our model-based predictive controller. It is also very useful quite often to generate data for inferentials. Usually that goes hand in hand with drawing frequent lab samples. It's also very important for us during the step test to learn about the process, and then mainly the controllability of the process. This helps us with our controller design, and which can be changed accordingly during the step test. It is very often that we have a functional design which we've done before step test, and due to all the information that we acquire during the step test, that we very often change our design by leaving out MVs, leaving out CVs, or maybe even adding other variables to the controller design. We often use the step test to identify non-linearities in our process. Every process is nonlinear, whereas the most APC programs that we currently use assume linearity. So with the design of our step test, we try to find, to some extent, those non-linearities in the system so that we can use our data for transformations. It's also very important to identify the sensitive operating region in our step test. It is very often the case that we start with making steps but we see no response, and then we move the process to a different operating region where suddenly the responses appear, or they change in size due to the non-linearity of the process. We know that mostly normal operating data is not good for model identification. That is because there's a lot of correlation in the data. For example, when operators increase the feed to a furnace, they would change at the same time the fuel gas pressure at the same time in about the same ratio. And this would make the data very inconvenient to use for model identification. Very often the moves that the operator make are way too small. We cannot really see from one step to the next the process responses that we want. And very often there is a lot of feedback in normal operating data, which is really detrimental for model identification. What is the requirements of a good step test? Firstly, we would like to maximize the richness of our data, and then of course we would always like to minimize the time in which we acquire that. That is usually because of budgetary constraints on our projects. There is limited amount of time that we can spend on the step test, not only because time is money, but also because a step test is a period of increased instability and risk on the plant. While we are doing our step test, it's basically an operation that is not normal to the operator, and they would usually prefer us to come and do our thing and get out of there as quick as possible. Also because very often a lot of product giveaway is tolerated. For example, we could often ask that the reduced feed rates be run while we do our step test. Many of the plants that we have seen in the past has a throughput rate of way above 100% of design, but very often this is running or pushing so hard against the constraints of the plant that it is not really good for acquiring good step test data. For example, valves may be fully open, we may be pushing right against the quality constraints, and therefore we often prefer that the throughput is reduced slightly, let's say to 90 or 95%, to make the step test easier for us. The steps must be uncorrelated. Typically we would say step only one area at a time, but that could be very time consuming. So that is the reason why NVs have to be stepped together, and then in such a way that there is some randomness in the step test pattern, that there is no correlation between the inputs of our model, which are the NVs or the DVs, and then also that we do not always correct for a certain step that we have made in the same way and in the same time span. For example, when we make a certain step, that could have a certain influence or response from one of our dependents, which could be a product quality, and then we could be using another of our handles to correct for that excursion of the quality, always in exactly the same way or at the same time after we have made the initial step, which introduces correlation into our data and which is once again at the end detrimental to good model identification. Another requirement of a good step test is that we excite all frequencies. Of course, our step test plan has to be related to the steady state of the actual physical process, which means that we would want a number of very long steps which approaches the steady state of the process, and this is very important for getting a good model gain from our data, the gain between the inputs and the outputs of our model. And then of course we also want shorter steps for perfecting the dynamics of the model, which could be the dead time or the time constant if we're talking about a first order process. Important to note that every steady state step that we make, so every one of the long steps, is also applicable for getting good dynamics. Typically we want to see some variation in our step test frequency. Here is one example where, for example, we have, let's say in total 2 long steady state steps and a number of steps which would approach 1/3 of the steady state or 2/3 of the steady state. This is kind of a step test pattern that was traditionally very popular. At IPCOS we would often say that a minimum of 10 steps per MV would be about a minimum, but of course that is very dependent on the quality of the data. If we have good results very quickly, then a few steps could suffice. Whereas if we have a lot of process disturbances hitting us at the same time that we start our step test, 10 steps would not even be enough, and we would have to make more. More requirements of a good step test. We would typically step away from constraints. Okay, that could be a reduced plant load, or it could be away from product purity, just to prevent that we cross these limits. Still, at the same time, we want to be close enough to our process limits, so that our models are valid in this optimal operating region, because that is typically the constraints against which our NPC would push at the end, and therefore, as we have said before, all processes are non-linear, but we would like our model to be perfect in this operating region, namely close to the actual process constraints. We would always want to keep all valves and all cascade loops in control. That would be very important to the MVs that we are stepping, but it would also apply to other controllers, like, for example, level controllers in our process. Our steps should always be big enough so that the process responses are actually visible with the naked eye, which brings to mind the step to noise ratio. That should be big enough that we can actually see what is happening. At the same time, it should be small enough not to cause major upsets on the plant. We do not want our step tests to cause a negative sphere with the operators at an early stage of a project. We would typically step towards a sensitive operating region of the plant. That could be, for example, an over-refluxing distillation column. When we first reduce the reflux, we would see absolutely no change on the product qualities. But after reducing it for a number of more steps, we suddenly start to see the response that we require in our model. Another example could be analyzers that are running at or very close to zero due to over-purification of the product. The first steps that we will do would be to bring those analyzers into a region where we can actually see something happening. Okay, we will typically step in the region where our APC limit would be. So, for example, when we're talking about a quality limit that will be controlled in the APC application at a limit of 100 ppm, then we do want to make sure that we generate sufficient data around that exact value of 100 ppm. At the same time, we want to generate enough data so that we are able to transform the nonlinearities in our process. Those could be valves, those could be analyzers. So even though we would be controlling at a value of 100 ppm, we also want some data at a much lower value. And if allowed by the plant, some data points at a higher value even. Here we see a number of step test patterns that could be applicable to certain processes. The first one there would be typically where we have agreed to stay around the current operating region. So we would step down by half a step, then up by a whole step, defined by the size of the step that we need to actually see the responses. And after our steps have been done, we will tend to end at the same value that we have started. In the second case, for example, we're only stepping up, and that could be due to where the constraints are. In this case, there is some limit against which we are stepping, and we design our step test so that we move away from a particular constraint. The staircase patterns, as we see there, number three, that is typically applicable when we want to find a certain nonlinearity. For example, we want some data of a valve constraint that we would, where we are typically operating at, let's say, 50%, but we would also want some data around 100% and be able to transform that input by using the data. So we'll apply these steps and take it from 50 up to 90 or 100% and look at the at how the data changes incrementally between these steps. That is, if the process allows, of course, and if it's really practical at all to make such steps. Number 4 could be an example where we've stepped up, we saw no response, we stepped down again, and then we realized that we are in a non-responsive region. And the way to get out of that is to keep on stepping down until we see at one point a good process response. Let's talk about the prerequisites for a typical manual step test. The first phase in our APC projects are typically an assessment of the base layer instrumentation and control. We typically call that the pre-test. This means tuning of all PID loops that support the APC and also other loops that play a role in our APC scope. Identifying problematic valves, for example, for stiction, hysteresis, filtering some noisy signals, verifying that all the analyzers are working fine. And then we would typically specify supporting base layer structure, typically looking at the modes of the base layer loops to determine the step test mode, which is basically the mode that we will eventually have supporting our APC application. In some cases, we could be adding new controllers or cascades, for example, a furnace outlet temperature or a duty control. We often come to a plant and see the operators adjusting fuel gas flow or fuel gas pressure to a furnace themselves. Our best practices would then advise us to get such a furnace outlet temperature on the base layer to support the APC, which will come on top of that. In the distillation column, for example, we could have a tray PCT control with pressure corrected temperature that would set either the reflux flow or the reboiler duty flow. In the case of a compressor, for example, we could first decide to build a suction pressure control that set the speed of the compressor, which would eventually be used as the manipulated variable in the APC. Before we will start our step test, an important prerequisite is the actual functional design specification, because this will tell us which are the MVs that we need to step, which are the DVs that have to be watched or stepped in the case where that is possible, maybe in an indirect way, for example. And also that will tell us which are the CVs, the constraints that we will be watching for. Some of them to eventually include in our APC as control variables, and in other cases just important downstream constraints maybe, which we have to keep in mind anyway. The FTS would tell us what our control and optimization strategy would be. And of course, a step test should be designed around this, as we want to make sure that we collect enough data around this optimal region towards which the APC will eventually be pushing. All of this whole functional design has to be verified during the step test, and changes will be made according to what we discover during the step test. Another prerequisite would be an expectation model matrix. Before we start on this endeavor of a step test, we want to have a good idea of where we expect the models to be. And very often it will go exactly according to expectation. In other cases, some of these models may not appear. In other cases, we will find models where we did not expect it initially. And then it's very important that we have data collect running, of course, while we do our step test. Usually at the 1 minute frequency, if we're talking about most of the chemical processes that we work on, and that has has to be done via a functional OPC, so that has to be implemented and running already when we start our test. Of course, for an automated test, all these apply, all these prerequisites of the manual test, but then there's also an additional number of prerequisites. For example, the APC hardware has to be already installed and networked. The APC software and licenses have to be available and installed already when we start our step test. We would need a functional OPC connection that can read and write. Very often when we come to a plant, there is an OPC that can only read, for example, to populate a plant historian, but it cannot write. So in this case, we would already need the full functionality when starting our test. And then the DCS switch logic, which is being used for turning the controller, subcontrollers and MVs on and off, as well as watchdog functionality. That has to be implemented already so that we can actually use our auto-tuning application and switch it on and write the set points automatically to the MVs on DCS level. Very often we need customized logic for this, and that is also very dependent on what DCS we are using. Very often we need custom operated displays on the DCS. In some cases there is already some web-based application that we can use for view, but in other cases we need additional operated displays so that we as engineers and the operator can see exactly what our auto-tuning application is doing. Very important is that we require seed models. For an automated test application to work, let's say at the level where we are doing a step test against actual process constraints, then we do need a reasonable quality of models that we already have in our application before we can actually allow it to step automatically. So in the case of a new project, that makes it clear that we do need to start with some manual steps because we know already that historical data is less reliable for getting these seed models. In the case of a project revamp, for example, we just use the existing models. So auto testing is, in this case of a project revamp, really ideal. Also, prerequisites for an automated test, the APC configuration files. There's quite a number of hours of work that has to be put into setting up the actual configuration before we can then execute the automated test. It means the NV and CV limits have to be set up already, and that usually goes hand in hand with a lot of discussion with operations. It means that we need initial control tuning, both for the steady state functionality and for the dynamic features in our application. And then there's usually quite a lot of auto tester tuning that also has to be set up and tested and simulated before we can actually come back to the plant. This requires a lot of knowledge about the actual process dynamics, which we should usually get from some manual stepping or even during the pre-test. We should know the step frequency that we want to set up, and of course the step sizes. And then it's also very important to know which MVs we would like to step together in the same step test pattern. And in the case of levels, we want to define already our primary and secondary ramp handles, which will be set up to actually keep our levels in check. So let's think about the pros of automated testing. There's quite a lot of pros, otherwise people would not be spending so much time on getting these applications online out there into the market. Many of the benefits are obvious. It is actually so that we do get richer data and better quality data in a much shorter period of time. So I would say most of the applications that I've worked with, this is indeed the case. Automated testers are extremely useful to keep open levels in check. When we have open levels in a step test, it is very, very cumbersome to keep watching them. And levels are very important. We do not want to let them run empty or run over. So that's one of the main benefits, I would say, of automating a step test. And then, of course, keeping our valves and our slave loops from saturation. That is also something that is often neglected for some time during a manual test, and really influences the quality of the data. And so, yeah, very, very useful to have this looked after by an automated application. Okay, the big benefit of automated testing is that it actually overrides human nature to a large extent in our step plan. It makes sure that each MV gets its turn to be stepped. Very often when we do everything manually, we like to step the easy ones and continue on those and leave the more difficult ones for last. And then very often we realize on our last day of available step test days that we have neglected some of our MVs. And when you have set this up in an automated testing environment, this would make sure that each MV gets its turn. The usual, let's say, step test algorithms would introduce some randomness into our step test plan. This would typically make sure that uncorrelated moves are being made, but of course we have to be very careful of this. People can introduce correlation into a step test plan, but so can an automated testing program. It can happen that we have set up certain CVs, certain constraints in our application, continue making steps, and the application can keep on correcting for those steps with the same handles at the same time intervals, and in this way introduce correlation into the data. In this case, it is much more difficult to actually spot it than it would have been with manual moves. So it is very important to keep in mind that we set this up correctly and that we also do our post step test checks to make sure that our moves are not correlated. And then, of course, let's say a typical step test algorithm that is worth its salt would make steps over a wide range of frequencies. So it would introduce long steps and more frequent steps to really excite all frequencies and help us to perfect our model with regards to gain and with regards to dynamics. Typically, automated testing is very time efficient, and that is because once the operator has ceded control to our step test program, it really streamlines our effort to get these steps implemented. In case of a manual step test, it means going to the operator, working only through him, asking for a step to be implemented every time. And very often, depending on the conservatism of the operator and of the plant, this takes a lot of time. It could take a lot of time to get these steps implemented. Whereas once we have negotiated that auto testing will take place, basically the engineer is in charge of making these steps, either by the program or even through the introducing manual steps through the interface. Of course, a lot of responsibility now lies with the APC engineer, whereas before the operator was mainly responsible for the plant. So it gives us much more freedom in performing our step test, but it also shifts responsibility very much to our side. The cons of automated testing. Of course, there is a discomfort of the operator and of the plant, and initially that could be quite a big effect. I guess usually after some time of auto step testing, when we have set it up correctly, this discomfort will disappear and the operator will get used to the idea of some program making steps on his plant. Very often steps can be made at exactly the wrong time. Mainly, for example, there could be some plant disturbances, there could be some events on the plant that we know of, and that would have prevented us from manually either making the step at a different time or changing our step test plan altogether. The automated program does not have this information, so it could often be that a step is being made at exactly the most unfortunate time, or that some MEs are stepped together or very close together at a time that it is not really convenient. This could amplify a certain disturbance in such a way that we would not want. Of course, we could go back to our setup and then change certain limits on the plant, change the frequency at which testing takes place. But of course, the fact that the step test application has to introduce some kind of randomness into the testing pattern always makes the possibility of this happening again just more likely than a manual step test. For an automated test, a lot of pre-work is required. We've seen already that when we look at the prerequisites of an automated test, that the hardware and software infrastructure has to be in place before we can actually do this automated test. Because we've done a lot of the setup already, a lot of the design of the controller, changes to the design can lead to some inefficiency and rework, which, well, you know, in the case of a manual test, we have a clean slate, so this inefficiency will not occur. Also, with an automated test, it is not often so easy to see with the naked eye the individual responses in our step data. Very often the MEs are stepped together or very close together. They are typically stepped at a higher frequency than what we would have done manually. And it is then not so easy for us to look at the data and learn what the responses actually are for each ME to CD combination. So whereas typically the process learning curve for the engineer is very steep during a step test, it is less obvious when we do the tests automatically. The pros of manual testing. Of course, the most obvious is that we are able to start earlier. There is not much pre-work that has to be done. This is ideal when there is a delay in the delivery of the APC hardware or even the software. It is also ideal when the switch logic that has to be implemented on DCS level proves to be more complicated than foreseen, and this happens quite often, I would say, depending on what exotic DCS we are working on. Of course, it is always very easy to change design. When we start the step test, in this case, we still have a clean slate. We have our functional design, which is written up, and there are always changes required after step test. These can be very easily implemented then. Of course, we know that the operator implemented steps are usually more conservative. The operator knows his plants. Well, some of them could be too conservative. That also happens, or they could require authorization from a few levels above them, which makes it very cumbersome. But the fact remains that they know their plant best, and we should actually see this as a benefit of a manual test. Because we are doing the steps manually, the steep process learning curve that I've spoken before does actually take place. We make the steps, we look at responses one by one, and we learn very much from that. About the plant, about controllability, about non-linearity of the plant. Okay, we also have a lot of flexibility when we do a manual step test, especially over non-linear operating region. So whereas an automated test has to be set up before, between limits, stepping up and down, there's kind of a preconceived idea of how it will step. Whereas manually we can make staircase patterns to step over nonlinear region, which is ideal for getting transformation data. In some cases, we need to get the required process response by making two steps after one another. It could be that, for example, we are looking for a product quality response, for which we need to make a big step, but because of some level that runs over, or a valve that goes to saturation, we cannot implement the step in one go. So we have to do it in two steps. And this is typically much easier done by implementing manual steps. Well, the cons of a manual tests, I think we've probably touched on many of these topics already. We have to ask the operator for each and every step, and very often that can take some time, because depending on the culture on the plant, the operator would not immediately execute that step, but ask his supervisor for authorization, and the supervisor would ask someone from the next level. And this would cascade down again to the operator, and if this happens for every step, it could be much more time consuming than automated tests. Operators, even though we usually ask them to communicate all correcting moves that they make to us, could still on the fly behind our backs go ahead and make some unexpected correcting moves. Of course, auto testers do that as well, but we as an engineer have much more control as we set up the application ourselves. Of course, while manual testing, we have to watch the levels extremely carefully. And depending on the size of the capacity that we are talking about, this could be a very time-consuming exercise. We have to monitor the saturation of valves and of slave loops ourselves all the time. And then we have the tendency to leave some areas that are a bit more difficult to test, or could create some process disturbances that would make us unpopular with the operators, to leave those for last, and then in the end discover that we've made too few steps on those. We do have a tendency when we do a manual test to focus on long steady state steps, because we would often make step, and if after two steps the responses look very different, we would like to get like visual verification of what it is. So we do often tend to focus on long steady state steps and supplement less in between with quick steps when we do it manually. And then of course there's always a tendency to introduce correlation in our step test pattern. Of course we can always then at the end decorrelate the data that we have by stepping only one MV at a time for a certain period of time. So what would the ideal step test procedure look like? I would say for a new project there is no fully automated step test. But if the automated, if the tools for an automated test that are available, if those tools are mature enough, here I could, for example, name Asmtech's Smart Step, then please do use those tools and try to learn to work with them, even though there is kind of a discomfort at the beginning. It is always worth your while in the end to try and use these tools and gain some experience with using them. Of course, that is unless the project flow dictates otherwise, and that could be, as we have mentioned before, the case where there is some delay on the delivery of the hardware or the software infrastructure. Typically, we would start with a fully manual test. This could even be during the pre-test phase of a project, and then we will progress gradually towards a fully automated test. I would typically step the levels manually at the very beginning of the project, even during the pre-test, because that allows early inclusion of the levels in the automated test and really takes a lot of problems out of our hands. I would typically only define a primary ramp handle to be used in the automated test to keep the level in check. That often makes it very much easier. We would also start with a manual test to find a responsive region in which we want to continue our test. We do that manually, especially if we know of the possibilities before, like reducing the reflux on the distillation column until we do actually see the trade temperature showing good responses. And then at the very beginning we will do some manual steps for finding the important valve models. This also applies to slave loops in the case of a cascade on DCS level. Once again, it's very convenient to include these models, and it will typically just be the most important models. Let's say if we are talking about a certain flow controller, we will just add the primary model for keeping the valve from saturation in our automated test application. This allows for early inclusion of the valve models in our automated tester to help us guard against controller saturation during the rest of the step test. After we have set up our auto testing application, it is often very useful to switch it on and have our MVs, our model inputs, in the RCAS mode, and then do the manual steps that we planned to do it actually through the auto testing interface. This gets the operator familiar with the procedure of an automated step test very early. It also breaks the ice in terms of the fear that the operator may have of bad things happening on his plant due to auto testing. Typically, we will start with longer steady state steps in the auto tester. If we do not know the steady state of the plant already, then this gives us the experience to actually determine what the maximum length of steps should be. If we have an application that allows for a sequential step algorithm for only one MV at a time, we would typically start with this and then at a later point move on to an algorithm where all the MVs are stepped together in a randomized pattern. After starting with longer steady state steps, we would be able to calculate our seed models depending on the scope, of course, after about 1 or 2 days, I would say. After that, we will activate only the key CVs in the application. There is never a case where you would get models for all the CVs and just switch on all of them. You would make intelligent choices and practical choices at the same time about which CVs that you want to step against and which CVs that you actually want to enable them to influence the step test pattern. Only the key models of each active constraint will be included. The less important models or the smaller models should not be included. That would typically mean only the 1 or 2 key models for each and every CV. And for the levels, as I said, I would typically use only the primary ramp handle model and let it correct for the rest on feedback. It is a gradual process of increasing the CVs that are made active in the step test pattern, and very often they tend to be only the few that, as I said, due to intelligent practical choices we do actually make active, are the ones that we keep on at the end. It's never the case where we just put on all the CVs during an automated test. So after a few days, we will start using our multi-MV stepping algorithm, which is usually made to introduce random steps over different frequencies, which is the tool that actually helps us to save a lot of time by the actual pattern that it introduces. We have to think very carefully about the division into test groups. That means the MVs that means which MVs we will be stepping together or include them in a certain step test pattern. It could, for example, be useful to include all the ramp handles for controlling levels in one test group, so that in this case we could suspend these flows. If we look at a process where there's a few distillation columns in a row, it could be useful to keep the feeds, which are the ramp handles controlling the levels, in a suspended mode, and to have them step only when one of the levels tend to be at the limit for some time. We could then choose at a later stage to step them specifically to improve the models for the levels themselves. So it's very important, the point I want to make, it's very important to think carefully about the division into test groups of the different MVs. I would say unsupervised, totally unsupervised automated testing should be possible after a few days. That would mean when the main CVs have been put active in the application. Let's say, once again, depending on the scope, we should be able, after about 5 days or 6 days, to be able to cut down on the amount of test hours that we actually spend on the plant. We might even be able to avoid night shifts by letting the application step for us. Of course, very good preparation of the operators goes hand in hand for this. They would always have to know which are the variables that are stepping, what the limits are. Typically, we would say if there is uncertainty, do the unsupervised testing in a sequential mode, in a mode where only one MV would be stepping at a time, just to give more of a comfort zone to the operator and prevent him from interfering with the step test himself. It is very useful to give the operator an interface by which he could monitor the test, especially seeing the expected steps to be made. It is very often that a step test application shows which steps it intends to make in the future, and then also and possibility for the operator to adjust the auto testing behavior, maybe by making some manual steps through the interface. Of course, there's a balance here. We don't want the operator to be involved in the step test too much, but we do want to give him this possibility to at least know what's going on and to be able to predict that that things are going well, or to be able to adjust if they are not going well. We would regularly run the modeling cases and then refresh our models, I would say in the beginning once per day, for the CVs that are being active and in the step testing application, and also to be able to make active an increasing number of CVs, which we know are active constraints on the plant. Finally, towards the end of the test, we may often find that we are lacking data for transformations, and it could often be valuable right at the end to make these steps manually. For example, in the case where we need to make staircase patterns, to find to generate transformation data for some of our valves or our analyzers. It very often happens that we discover this towards the end. So I guess we do need to leave a day or two at the end of our test to implement a number of manual steps, whether we do it through the step testing interface or manually, doesn't really matter, but just to generate some data which we know are well, difficult to generate through auto-testing. Okay, this leaves some time for questions from our attendees. Usually we would we would find those through the chat window, but because this is a re-recording of the revamp, I will just take some of the questions that have been posed to me before and after, sent by email. So one of the questions I had are about the auto-testing packages that are currently available and with which we have experience and which can be recommended. I would say typically AspenTech's Smart Step is quite a good application, which we use quite often. It's probably one of the most mature auto-testing applications that exist currently. I've recently seen that the new platform used at Shell, also distributed by Yokogawa, PACE, Platform for Advanced Control and Estimation, it is called, also has an auto-testing feature where it actually makes use of process models and step tests against active process constraints. At IPCOS we are also working on an auto-testing application currently, and it is being tested at a number of the projects we are working on. Another question, how good do the seed models have to be? The developers of auto-testing packages would stress that these are very robust applications and that the models do not have to be all that perfect at the beginning. I would say that you could, from experience, I would say that you could tolerate a gain error of about 20 to 30%. So, well, generally you have to make sure that your gain is going in the right direction and that it is at least in the size range that you would expect before you would ever attempt putting that into auto-testing application. Important to know that you will typically only keep the very strong relationships, the very strong models in your auto-testing application. The smaller ones would not feature, or the secondary models. So for each CV that you make active, you want only the models to the dominant handles to be in there. Okay, so to conclude, I would say 20 to 30% model error is good. That concludes our webinar for today. We've spent quite well. We've gone a bit over our time already. I would thank you for your participation once again, and I want to point to the fact that there will be a next webinar. The date and time still have to be announced, and the topic would be APC on hydrogen networks. The benefits of APC technology are not as well known for hydrogen plants and hydrogen networks, and in this webinar we will present a case study of such an application and the benefits generated for the client. This recording will be available on IPCOS's YouTube channel, and if any more questions or comments arise out of this, please email Christian Moons, also if you would like a copy of the presentation. Thank you very much for your time, and hope to see you at the next webinar.